We're going to talk about past climate, transcend, and then we're going to talk about future climate. So for chapter 10, we will start with the geological time, the cenozoic, the quaternary, the Anthropocene. So through geologics, although geologists recognize the occurrence of past ice ages in the 1840s, the study of climate change only began in earnest in the 1950s to 1960s through Roger Bevell. Since the 1980s, there have been major advances in our understanding of the nature and reasons for climate changes. These advances have been made possible through the development of new observational tools and hypotheses and the use of global climate models to simulate past climatic conditions. No knowledge of the climate of the past is of vital importance for a full understanding of present and potential future world climates. Analysis of past changes can help to reveal the underlying causes of global climate patterns. In this chapter, we will summarize our knowledge of geological time, the Cenozoic era, the Quaternary period, and the Anthropocene, when human influences on the environment became significant. It is worth pointing out that climate variability refers to the variation of global or regional climate about its mean state. The time scale may be decades or millennia, and the variation may be cyclical or irregular. Climate change refers to changes in the long-term statistics of climatic elements, the mean state, standard deviation, or frequency distribution. The time scale is at least several decades, but may be thousands of years or more. Climatic changes may be due to changes in external forcings, solar output, changes in the Earth orbit, volcanic eruptions, internal variability in the atmosphere, ocean cryosphere system, or anthropogenic human-induced forcing. Changes may involve an abrupt shift in the mean state, an increasing or decreasing trend over time, or a change in the degree of variation about the mean without a change in the mean value. Geologic time. The Earth was formed about 4.5 million years ago. It is thought that water was supplied by numerous cometary impacts, and by 4.2 billion years ago, there are oceans. The young sun was about 25% fainter between 3.8 and 2.5 billion years ago than it is now. Its luminosity increases about 6% per billion years, and it is probable that high levels of greenhouse gases, GHGs, carbon dioxide, and methane in the atmosphere prevented the water from freezing. The oldest rocks found in Canada date from 4 billion years ago. Figure 10.1 summarizes the geological time scale. Note the three different time scales. Life at the molecular level emerged around 3.7 billion years ago, and multicellular forms around 2.5 billion years ago, after which oxygen was formed in the atmosphere and the ozone layer developed. There were several severe cooling events in the Proterozoic early life era that are thought to have led to glaciations. The first occurred around 2.3 billion years ago, perhaps because oxygen in the atmosphere reduced the methane content, lessening the greenhouse effect. Two other glaciations that led to a state called snowball Earth, with global land and sea ice cover, are dated to 710 and 640 million years ago, MA. Perhaps associated with the formation of the first supercontinent of Rondina, animal life appeared and evolved rapidly after the second of these ice ages. Two supercontinents broke apart around 550 MA, and the geophysical mechanism of plate tectonics led the four new continents of Laurania, Bartia, Siberia, and Gondwana to move around in a process known as continental drift. This was first suggested by Alfred Wegener in 1912, but not accepted by geologists and geophysicists because they had not identified a mechanism. Finally, in the 1960s, the theory of plate tectonics was developed. Plate tectonics refers to the movement of 7 or 8 major plates in the oceanic and continental lithosphere over the Earth's surface at a rate of about 10 centimeters per year. The movement of one plate beneath another results in earthquakes and volcanic activity, as in the ring of fire that surrounds the Pacific Ocean is accompanied by sea floor spreading with the formation of new crust as long as the mid-Atlantic ridge. The collision of plates gave rise to mountain building during many intervals of geologic time that would have modified the global atmospheric circulation and the distribution of climates. Global conditions in the early Paleozoic era, 550 to 400 Ma, were generally warm, except for a short ice age in the Ordovician around 470 Ma, when the continent of Gondwana was situated over the South Pole. There was prolonged glaciation in the Permo-Carboniferous period, 300 to 50 to 260 Ma, that ended when the supercontinent of Pangaea formed. During the mid-Cretaceous period, around 100 Ma, high concentrations of carbon dioxide up to 1,600 ppm led to very warm and ice-free Earth and the age of the dinosaurs. It is apparent that global climate changes during early Earth history were mainly determined by changes in solar luminosity, atmospheric composition, and continental configuration. So geological time, we can see from here. And the geology of the Cenozoic era, so the timetable. Okay, now we're going to go through the Cenozoic era. So it's the third major eras of Earth history, beginning about 66 million years ago. So we now consider in more detail how would climate evolve during the Tertiary period, the start of the Cenozoic era. Cenozoic is Greek for new life, that began about 66 ma. See the lower panel of figure. So after the age of dinosaurs, when mammals evolved, information about climatic conditions during this remote past is derived from sedimentary rocks that contain plant and animal fossils and especially limestones that yield data on past carbon dioxide levels in the atmosphere. Conditions remained warm from 65 to 50 miles with no ice sheets, perhaps due to high carbon dioxide concentrations between 50.5 and 52 miles. There were several abrupt and extreme global warming events. These have been linked to intervals with high eccentricity in the Earth orbit and high obliquity exotilt that triggered massive releases of soil organic carbon that had been locked up in permafrost in the Arctic and Antarctic. These pulses of carbon dioxide gave rise to the warming episodes. Temperatures, especially in the deep ocean, then began to decline steadily with decreasing carbon dioxide levels. It has been suggested that this decrease was caused by prolonged chemical weathering of rock surfaces in the continent of Antarctica. About 33 MA, the climate of Antarctica changed from mild and temperate to glacial conditions with the buildup of extensive land ice on East Antarctica. It is uncertain whether this was caused by carbon dioxide levels dropping below a critical threshold or whether it was perhaps a result of the opening of the Drake Passage that allowed the formation of the Antarctic circumpolar current. This would have excluded warm waters from the seas around the continent. By about 17 March, the continents had drifted essentially into their present locations, establishing the modern patterns of circulation in the atmosphere and oceans. In the mid Miocene, about 18% ma, there was a warm period known as the Mersum climatic optimum, probably caused by high carbon dioxide concentrations in the atmosphere. Mean annual temperatures in Central Europe reached 22 degrees Celsius, compared with 10 degrees Celsius today. Then the climate cooled rapidly, and by 15 degrees Ma, there was already a large Antarctica ice sheet. But the Isthmus of Panama had not yet closed, and the different ocean circulation inhibited the growth of land ice in high northern latitudes. However, since about 14 Ma, there appears to have been perennial Arctic sea ice glaciation in the Arctic. Greenland appears to have begun around 3 Ma, when several global cooling steps occurred related to atmospheric carbon dioxide levels and the Panama Seaway finally closing around 2.9 Ma. This set up the present pattern of ocean circulation in the North Atlantic. The mechanisms involved the inception of Antarctic glaciation are still not well understood.